Our goal with these next few videos is to dive into Chapter 3. Chapter 3, we're going to talk about how do we find properties of substances that aren't like, say, pressure, temperature, and volume, things like internal energy and entropy. So we can go through and solve the first and second laws. That's what we're after. So let's talk about what are some tools we have to do that? Okay, now, before we get into a whole lot, really what we're going to do is by the end of the next block of lectures, we're going to get a real quick crash course in using the property tables at the back of the book. That's really kind of our goal is to get comfortable using those property tables. So, how do we get there? Well, we've got to start with how do those property tables work? What are the theory and the mechanics behind what those are actually describing? So let's lay down some theory and some terminology, and we'll work our way up to that. So the first bit of terminology here is you see this concept of a pure substance. So a pure substance just simply refers to a substance where it has a uniform chemical composition throughout. Um, it does not have to be pure oxygen, for example, or pure hydrogen or pure nitrogen. It doesn't have to be a chunk of pure aluminum. It can be an alloy. It could be a mixture. It could be, by this definition, um, just a second here. As I was saying, by this definition, something like concrete sometimes can be considered a pure substance based on this kind of very vague definition. Air, for example, the air that we breathe. The air in front of me, where I'm recording this video, is going to be very similar to the air that we would be breathing if we were in the classroom. It's going to be very similar to the air that you're breathing watching these videos remotely somewhere right now. It's high 70 something percent nitrogen, mid 20% something percent, mid to low 20% oxygen, and the remaining to get to 100% is some mixture of carbon dioxide, water vapor, and maybe a few nitrous compounds and hydrocarbons, right? But predominantly oxygen and nitrogen, and that's going to be very consistent throughout most parts of the world. So air, based on this definition, the air we breathe, we can consider to be a pure substance. We will encounter substances in multiple phases. There's two main substances, well, there's really kind of three main substances we're going to work with. One is water, H2O. As I mentioned earlier, before chapter 3, if we're in chapter 1 and 2, it's fairly safe to assume if I've got water that's in the liquid form. After we get done with chapter 3, it's no longer safe to make that assumption. You should have enough information to determine the phase of the water moving forward. So it's not uncommon. We will encounter water in a liquid phase, a vapor phase, or some mixture in between. It is rare, if not very strange, to encounter air where part of the air is in the liquid phase. It's not impossible, I guess, but in theory, the oxygen and the nitrogen are going to liquefy at different temperatures. So anyway, we're not going to encounter a liquid vapor air mixture, but we're going to work with a substance called refrigerant 134A. That's R134A. And we will always assume that R134A could be in the liquid vapor or anywhere in between phase. So we will deal with substances in multiple phases, and we'll also deal with some substances like air, for example. We'll almost always assume that air is going to be in the gaseous phase. Is there a difference between gaseous and vapor? Technically, yes. Practically, not really, but more on that to follow. Okay, if you've just recently had your chemistry class, you know that they are sticklers for the impurities, that if it's water, it needs to be purified, deionized, just pure water. Okay, that's fine for them. For us, we're going to assume that it's normal water. If you really purify water, it becomes instantly very reactive and it will leach whatever it can find, whether it's plastics, microplastics, whether it's salt, whatever it can find, it's going to dissolve a little bit. And then after a small amount dissolves, it gets pretty happy. So we just basically are going to assume that if I'm dealing with water, it's going to have some impurities. Um, these are typically stable this. These are typically negligible at low concentrations. So if they've given you water, if they want you to treat it, I have to concentrate as I write the word concentration. And I'm not going to get it in there, am I? There we go. Concentration. Um, now I've lost track of what I was saying. If the book wants you, or if I want you to treat water as anything other than pure water, if I want you to assume the properties are going to behave any differently, you will be given that information. Occasionally, you'll see like seawater. You'll see a problem. We'll have seawater as a substance, and because of its salinity, it will have slightly different thermal properties. For example, that's pretty rare. We had in chapter one, we had the example, or we had a homework problem where you had human blood, and that blood had a different density than, say, liquid water, even though blood is the major component of that blood is going to be water. So again, if that concentration of impurities or minerals or other things dissolved in that water are high enough to change its properties, you're going to be given that information. Okay. Um, what else? So just a little quick crash course of some basic material science here. Again, you've had chemistry before, so you should be familiar with the phases of matter. We'll just go quickly, very rapid fire crash course here. When you think about a substance that is in what we call the solid phase. So the solid phase, we are what we often tell students to do is to assume that those molecules in the solid phase are basically kind of attached to each other on springs. So the bonds that hold it in a solid structure are kind of like they're going to behave similar to how springs would be if you had little balls attached with springs to each other. You can kind of compress it and stretch it a little bit, right? Um, I just happen to have a guitar pick here that's kind of a quasi-solid. And so, you notice I can kind of flex it a little bit and then it goes back. So it's basically like springy. So that's essentially that's behaving just like it's a solid structure. Um, those molecules are not going to move relative to each other as long as you don't bend it beyond a certain point. If you bend it so far that it deforms permanently, then you've changed the alignment of those molecules. But you can bend it up to that point where those molecules start moving relative to each other and it behaves like a solid. You let it go and they go back to their original orientation. The molecules are in fixed locations relative to each other and they've got some freedom of movement, but not much. However, if I've got water in or any other substance in the liquid phase, so in the liquid phase, I've added enough energy that the molecules are no longer locked together in this what we call a crystalline structure. That's what forms a solid is what we call a crystal or a crystalline structure. Those molecules form a predictable pattern of arrangements in the solid phase. In the liquid phase, there's no order to them. They're I'm not gonna, I don't want to pour water out on my keyboard here. But those water molecules can move relative to each other. They're just in here somewhere. They form a clump. They clump together. So they're at a low enough energy state, they can't escape each other. They still clump together, but they form kind of a surface. They form a pool, if you will, of molecules that move together, or at least they'll move relative to each other, but they're going to clump and stay together. So they're kind of an intermediate energy phase. And if we add more energy to the substance, we can get it up to a vapor or gaseous form, where once I've added that much energy, those molecules are now free to move apart from each other. They are no longer their energy level is such that they overcome the attraction that keeps them together. So now they're just out there and they don't actually, the molecules aren't really technically even touching each other. There's often void space in between the molecules. The distance can be very large at very high temperature or very low pressures. Um, the motion especially in the gaseous phase, is very random. It's very high entropy. It's very unpredictable. So, in order to get these back towards a liquid or even potentially a solid phase, lots and lots of energy is going to have to be released to get them down that far. Okay. So, in visual form, you can see that there. It's a diagram similar to what you would find in the textbook. Again, in the solid form, just assume that they're kind of bound up together into a repeatable crystalline structure. In the liquid form, they just clump together. They stay together. In the gaseous form, they can move randomly about. Now, if what we're going to do is we're going to add some additional adjectives to some of these phases here. All right, so an adjective we would add to liquid is the adjective compressed liquid. So compressed or subcooled liquid, this is liquid that is not ready to vaporize. So your text will use almost exclusively the term compressed liquid. This is liquid that is not ready to vaporize. That density is going to be reasonably constant. So basically, for a certain amount of mass, it's going to occupy a very consistent volume. That will change in most substances, that will change a little bit with temperature, water especially. You can take liquid water, put it in the microwave, and heat it very gently. And then if you put it in a measuring cup and then you heat it up a little bit, it'll actually expand. So you get to a larger volume. Be very careful when removing that because, if you're using an old-fashioned measuring cup, it can actually superheat and you hit it, it boils over. So I guess don't do that. But yeah, density be reasonably constant. It will increase or decrease as temperature increases or decrease. Not a huge amount, but it does some. Again, it's not ready to vaporize. This last statement there, it's going to need more energy to get up to the vapor phase. But if we get it all the way to the saturated point, if it's saturated, if I'm talking about saturated liquid, that means it's saturated with energy. Saturated liquid is ready to boil. It's basically boiling. Saturated liquid is liquid that is right at the boiling point. The addition, if we add more energy, some will vaporize. Right, so it's right there at the boiling point. If I keep adding energy, some of it's going to vaporize. If I add enough energy, all of it will vaporize. Okay, but I'm going to have to get it over that hump, basically, to get it through the liquid vapor transition. I will have to add some additional energy. Now, I can also add this saturated adjective to the term vapor. Saturated vapor, that is vapor that is ready to condense. It's right there at the phase change point. So if it's saturated vapor, that means we've added enough energy to the liquid to get it all vaporized. It's all vaporized, but we've added just that amount. We've got it right to the vapor point, and then we quit adding energy. So it's saturated, but if it loses any energy, then some of the mass is going to condense back into the liquid form. It's right there at the point where it's ready to condense. So the loss of any energy brings it back down to a liquid phase. And then finally, and that's my timer, I had a pause a second ago, so I've got a second or two here before I hit 15. Finally, the term superheated vapor. This is kind of more like a gaseous phase, really. That is vapor that is not about or not ready to condense. We've added additional energy to get it beyond the vapor phase or beyond the boiling point, basically. So you've got down here compressed liquid, if we graph these, so to speak, right? Compressed liquid. I'm just going to write sat liquid, saturated liquid. You've got Then there's what we call a saturated mix, which we're going to talk about, if not this lecture, the next one. And you've got saturated vapor, which we've defined up above. That's vapor right at that boiling point, but it's all in the vapor phase. And then you've got superheated vapor. And as you move along, that is energy increasing going to the right. That's a nice stopping place.